In this lecture, we will consider some special cases of the applications of the saddle point integration techniques. And we will start by some not so standard case of the Bessel function in which both index and argument tend to infinity simultaneously. And in particular, we will deal with G index Z and argument Z with both index and argument equal and going to infinity at the same rate. And in order to consider the asymptotics of this function at large Z, we will make use of an integral representation So at this stage, it is not yet obvious what makes this integral special. And from the first sight, it belongs to our standard class of integrals of the form with large parameter lambda multiplying some regular function in the exponent. But in fact, let us try to analyze it in a standard manner, and let's see what happens. So this function has a standard notation of f of theta. And now let us search for stationary points. So we need to solve for an equation f prime of theta not equal to 0. So in order to do this, let us calculate the first derivative. F prime of theta equals cosine theta minus 1. And we see immediately that inside the integration domain itself, already on a real axis of theta, there is a stationary point. And the stationary point is theta equal to 0. Okay, now as soon as we have identified the stationary point, let us calculate the curvature of the f function at this point. So we need to calculate second derivative, which equals minus sine theta. And here comes the peculiarity of the situation, and in fact, we immediately find that this second derivative evaluated at the stationary point vanishes. So here we are. As before, we were dealing with a situation when this function was quadratic in deviations from the stationary points, and now we see that this quadratic part vanishes. And of course, this situation can be quite easily dealt with. And what we need to do is just to look for the next term in this situation. This is a third term of the Taylor expansion, and calculate third derivative evaluated at phi naught. So third derivative itself is just minus cosine theta, and evaluated at theta equals theta naught, it is just minus 1. And so we end up as an intermediate result with the following expression: f of theta in the vicinity of phi naught, which is just 0 at this situation, equals minus 1 over 6. This is just third derivative and 3 factorial multiplied by theta minus phi naught cubed. Or in this case, this is the same as minus 1 over 6 theta cubed. And this is all what makes this situation peculiar to some extent. And let us now analyze this expression. What we are doing is integrating in theta. This is plane of theta. And the integral starts from minus pi and ends at pi. And we just have identified a stationary point, which is in the middle of this interval. And we know the behavior of this exponent in the vicinity of the stationary point. But before proceeding, we need to realize what is actually going to be the more dominant contribution. So notice that this integral also is different from most of what we did before, in fact, by the fact that it does actually have contribution from endpoints. And in principle, similar to what we have had on the real axis, we need to convince ourselves that contribution of endpoints is smaller than contribution of the stationary point itself. So having this in mind, let us start from estimation of the contribution of the stationary point and then compare it of what we would expect to obtain from the endpoints of the integration domain. And concerning the stationary point itself, we need to, as usual, we need to find the directions of the steepest descent of the exponent in the integrand. So for this, we need to analyze this expression. So in the exponent, we have so in the vicinity of the stationary point, we have this expression for the exponent. A standard analysis immediately shows us the directions of the steepest descent come along the dashed lines, where both of these angles are pi over 6. And afterwards, we need to convince ourselves that the proper proper deformation of the original contour, which used to go along the real axis, is something like that. And the most important feature of this contour is that starts from proper start and end points of our original integral, and ends up at the stationary points. And the lines of the integration starting from minus pi smoothly, the contour smoothly fits into the steepest descent direction, and then it smoothly leaves it off and then sticks to the endpoint. So let us now postpone the estimation of the contributions of the endpoints and evaluate the integral in the vicinity of the stationary phase point. So, and we need to take this expression and substitute it to our original integral. As usual, we may safely extend the integration limits to infinity. And actually, we probably could easily evaluate this integral as it is written, but let us now separate it into two parts and perform the change of the integration variable in order to keep theta along the steepest descent direction. So it's convenient to split this integral into two parts, say lambda 1, gamma 1, and gamma 2. So at each of the parts, the change of the integration variable is as follows. So at gamma 1, we say that theta equals exponent of 7 pi over 6 I times z, with z going from minus infinity to 0. And at gamma 2, theta is exponent of minus pi over 6. Sorry for the notation is could be probably confusing, so let me use t instead of z. And this is exponent of pi over 6 times t, again with t going from 0 to infinity. After this change of the integration variable, the integral becomes let us first see what happens with the expression in the exponential after such a change of variable. So let us do this simple exercise somewhere here. Тогда я не помещаюсь, к сожалению. Сейчас, погоди, а я подумаю, могу ли я здесь поместиться. Наверное, могу. Тогда сделаем паузу, я чуть-чуть покомпактнее вот это все напишу. So after we have realized how the contour should look like, let us parameterize each parts of the contour. So at gamma 1 part, we would write theta equal to exponent of 7 pi I over 6 times t, with t going from minus infinity to 0. And at gamma 2, we would write theta equals exponent of minus I pi over 6 times t, with t going from 0 to infinity. With this in mind, let us see how the expression in the exponent modifies. So it becomes, on the left part of the contour, it becomes step by step. Андрей, прости, вот я так мелко никогда не писал. Это видно вообще? То есть это уже еще приемлемо, да? So, and let us now analyze the expression in the exponential. So it would become minus 1 over 6 times I times exponent of 7 pi over 6 t cubed. And this is nothing but, to analyze it, let us first look at the exponent. What it does, it gives us 21 pi I over 6, which is nothing but imaginary I. So after everything combined, it becomes minus t cube over 6. And the same happens here. And this is minus I over 6 exponent of minus ip over 6 times t cubed. Again, this has becomes minus I, and everything combined, it gives minus t cube over 6. So as a result, we may now combine everything. And the result would be the following. So z of z becomes 1 over 2 pi exponent from 0 to infinity of minus t cube over 6 dt. And there is also a factor which arises both from the fact that there are two contributions, each of them are coming with certain phase factors appearing from the change of the variable. And these phase factors are as follows. This expression can actually be slightly rewritten, and it's convenient to, and this integral can be expressed in terms of certain gamma function. So let's look at these two stages one by one. So first, to evaluate this integral, we will make a change of the variable, which will render the expression in the exponential linear in t. So let us again consider these two steps one by one. And first step is to evaluate this integral from 0 to infinity, exponent of minus t cube over 6 dt. We make a change of variable, t cube over 6 equals u. And this renders this integral into the following form. So expression t, from this expression we have t equal 6u to power 1/3, and as a result dt is 6 to power 1/3 du over 3u to power 2/3. And hence what we have here is 6 to power 1/3 over 3u to the minus t over 3 du. So at this stage it's already clear how it will express in terms of gamma function. Let us postpone this step. And the last step in the simplification is to rewrite this this expression. And in order to make more clear what does it mean, it's convenient to factorize and to rewrite it in terms of certain cosine, so that it becomes So let us now, after we have figured out what the contour should look like, parameterize it and perform the direct evaluation of the remaining integral. So for gamma 1, we will write theta equal exponent of I pi over 6 t with t from minus infinity to 0. And for gamma 2, we will write theta equal to exponent of minus I pi over 6 t, with t going from 0 to infinity. With this in mind, the whole integral for z of z becomes as follows. Then the next step is to combine both of the contributions from gamma 1 and gamma 2, and as a result we come to the following expression. This is nothing but phase factors coming from the change of the variable, and the remaining integral is going from 0 to infinity of exponent of minus t cube over 6 dt. And the next step is to evaluate the integral in t, and this is quite a straightforward step. Let us demonstrate the details here. So the integration is achieved by change of the variable t cube over 6 substituted by u, and it means that the integral from 0 to infinity of exponent minus t cube over 6 dt becomes and here there is derivative of the back substitution, which is nothing but the last step is to come to the following expression: 6 to 1/3 divided by 3 and exponent of minus u times u to minus t over 3 du. And this is nothing but a gamma function with a certain prefactor. So finally, we may combine everything together, having in mind that this is nothing but cosine, and as a result, z of z becomes 1 over 2 pi times and times 2 cosine pi over 6. So this is our final result, and to understand the meaning of the endpoints in this integral, let us make a brief estimation. It will be part of your homework, but let me give you a clue. So now what we have calculated is contribution of only the middle point of the integration domain and its immediate vicinity. But in fact, there is of course also a contribution of the endpoints, and its value, its magnitude, can be estimated by the integration by parts. So in fact, you may consider this integral in the vicinity of the endpoints, and then replace the expression in the exponent of the integrand by an approximate expression valid in the vicinity of the endpoint, and then perform integration by parts to show that the contribution of the endpoints will be actually proportional to 1 over z. And this factor, let us restore the z dependence here. It comes from all of the exponents, and as a result, what we have here is 1 over z to power 1/3. And compare the contribution of the stationary point with respect to compared with respect to the endpoints tells us immediately that they will compare to each other as 1 over z from the endpoint versus 1 over z 1/3 from the stationary points. So in this case, the contribution of the endpoints can be safely neglected.